Hey, so we had a lot of questions about this problem from the problem set this week, so I wanted just to go through and hopefully try to clarify a few things. So you're asked to find the matrix S squared, and you're using the basis, these composite states. So the first thing is that the matrix you're going to make is going to be a 4x4 matrix. And so here's my sort of little picture of that matrix. And each one of these is going to be a matrix element. So for instance, the A11, now this is just how I decided to do the basis, is going to be the matrix element of the spin up, with the S square sandwiched in there of the spin up. And then, for instance, this A44 would be the spin down, S squared, spin down. And there's no sort of set way that you have to do this, but I just decided to make the middle ones look like this here. So hopefully that helps to clarify a little bit. Now, when you're actually doing this beast, that's where it also can get pretty tricky. And so here, this is S squared. Again, S squared, the S vector is defined as the S1 plus the S2. And so Griffiths writes this out, and Griffiths does this. This is equation 4.177 in Griffiths. So one thing is he goes through and does a very similar thing to this. So hopefully you can find that helpful too. But when you do this multiplication there, you come out with three terms. So you've got the S1 spin squared vector, the S2 spin squared vector, and then the cross terms, which work out to be 2 times what works out to be the S1 vector dotted with the S2 vector. And so when you're doing these matrix elements, the key part of that is to be able to take all this stuff here, the way we just wrote it out there, like this, and I'm going to try to keep consistent with Griffiths notation. So this is our way we can express S squared, because we're acting S squared on the composite states, and so we want to make sure we can express the X squared in terms of the composite operators. And so I'm just going to go ahead and do this for the spin up. Now hopefully you can see that what this works out to be is it would be so S1 squared, and so you just distribute this piece to all the 3 different pieces. Okay, so it's 3 terms. I multiply the 3 terms by the ket spin up. And the way it works is, at least in my mind, the first 2 aren't that bad. It's the third one where things get a little bit nasty. So we'll sort of unpack that one in a second. But so this is S1 vector squared. And so remember, when you write it that way, it only acts on. So this one's only acting on that first spin. This one's only acting on that second spin. So this is going to give us back 3 over 2 h bar squared. And so this is because it's the your S squared vector 1 is acting on just a spin 1/2 particle, and this is an eigenstate of that. So you get 3 h bar squared over 2. This one's the same thing, it's just working on the second particle, so 3 h bar squared, and of course this is over 4, beg your pardon. Again, times the spin up and the spin up. And then again, this is the one where things get a bit more complicated. But so for those first 2 terms, it'll work out like this for all of your different pieces. And so now let's go through and try to see if we can make a little bit more sense of this dot product. So there's different ways to express this. If you look around, you might find a different way that works a little bit better, but I'm just going to stick with what Griffiths did. And so the simplest way to write this is just to literally take the dot product of S1 and S2. And so that gives us SX of 1 and 2, SY of 1 and 2, and SZ of 1 and 2. And again, we're all operating this on that spin up ket, at least in this particular case here. And so if I write this out, it would look something kind of like this. SZ. Sometimes just writing all these pieces is a lot of work. Okay, and so it's these. Now it's this last term turns out to be 3 terms times this. So again, what I'll do is I'll write it out and distribute it, just to be super clear with what we're doing on all the pieces here. There's a 2. Another 2. All right, so now let's start doing this. Now, this one here is probably the easiest because the spin up is an eigenvector of these guys. So again, the number 1 only works on the first one, and the number 2 works on the second one. They're both spin up. So this guy here will give us 2. We'll get an h bar over 2 from that spin up, and an h bar over 2 from that spin up. Okay, so that one's not too bad. Now these are the ones that are a little bit tricky. So we're going to use our trick where we expand this composite state, sort of like this here. Okay, so we can think about this thing as looking like this here. Again, the SX2 doesn't act on the SX1, so we can just sort of slide in. So you have the SX1 times our number 1 particle, and the SX2 times our number 2 particle. Now, a lot of ways to think about this, but probably the best way is just to go and think about, well, when we have our SX acting on either a spin up or a spin down, we can think about that in terms of a matrix. And so this would be our SX matrix, the form of it. And then since it's spin up, it would be 1, 0. If I work this out, I get h bar over 2 times 0, 1. So the effect of this operator on here, if I was to go down here and do it, it should give me 2. And so this guy on this one would give me h bar over 2 times then the spin down. And then the same thing over here, this would give me h bar over 2 times the spin down. So they're different particles, but the actual math for those works out to be exactly the same. And you can do sort of the same thing then for this next one. And of course, in this case, the way I would write this out is you'd say 0, negative I, h bar over 2, h bar over 2, I, 0. So this matrix, again, has the complex I, so it's a little bit nastier, but it's the same sort of idea. And when I do this, I'll come out with I, h bar over 2 times 0, 1. So again, these are not eigenvalues of the y and the x operator, but we can still go through and operate on them and get a result. And so when I'm done with this one here, I'll get 2, and then, so this would be I, h bar over 2, spin down. So again, it makes it go spin down, and then I, h bar over 2, spin down. And so after all of this business, I get something along these lines here. And if you look at these two guys, when I multiply the I times the I, this turns into the negative of this. And so what should happen is that in this case, these two guys cancel. So this whole operation on spin up should just leave this here, 2 times h bar squared, and that's of course a 4. Make sure that looks better. So we can come over here and then just remembering everything that we had. So when I applied the S1 operator, I got 3/4 h bar squared. When I applied the S2 operators, I got 3/4 h bar squared. And then this one here, right, we just got 2 h bar squared over 4. So all of that times the spin up. When you add these, it's 1, 2, 3, 4, 5, 6, 7, 8/4, or 2 h bar squared, which is good because we want to get, right, h bar squared times s plus 1. In class, we talked about how this is a spin 1 state, so we actually get what we want. So that's nice, and that's what Griffiths does. He's kind of proving that you get this. But for our cases, we want to figure out then how this helps us calculate our matrix elements. And so in this particular case here, so the s squared operator, so this is s squared operator times the spin up gives me this. And so then if I sandwich it here for that first matrix element, it comes out to be something like this. And so this would be 2 h bar squared. And so if I start making this matrix, right, this big 4x4 matrix. So I just solved for that piece there. But what I also did is I showed that all these pieces here have to be 0, right? Because there was no, there is, so this operator times this guy gives me the constant 2h bar squared, right? And so if I apply the sandwich of, say, something like spin up, spin down, spin up, s squared times up, up, I can argue that that has to be 0. So that starts us calculating this matrix, and so hopefully that gives you some help to go through and figure out the rest.